For this next one, I'm going to walk you through what's in the textbook. Our theorem supposes that F is a vector field that's continuous on an open connected region D. Let's pause for a moment. Since D is open, it means it doesn't contain its boundary points. And so any point interior to D has, we can create a neighborhood about it that is still also contained in D. Think of it like an open interval on the x-axis. If F is that continuous vector field, then if the line integral over C of f dot dr is independent of path in D, then F is a conservative vector field, and what that means is there exists a potential function lowercase f such that del f is equal to f, the conservative vector field. Now the way we go about doing this is we're going to define f of xy, the desired potential function, as the line integral of f dot dr, and we're going to go from AB, a fixed point, to a random point xy in our region D. And we're going to do this by taking two paths. One of them is C1, which takes AB to a point x1y, and the stipulation here is that x1y is inside of the neighborhood about xy. And then C2 is a horizontal path that goes from x1y to xy. The y's are the same, the x1's are not. Got into an argument with the iPad there. Okay, and we can choose any of these, any paths actually that go from AB to xy, because by assumption, the line integral over C of f dot dr is independent of path. So we take that line integral and we split it up into C1 and C2, and introducing limits of integration here, for C1, we had that starting point of AB and the ending point of x1y. And in evaluating this integral, since a, b, and x1 are constants, the only variable is y, and so we see the first of these integrals, that's this one here, doesn't depend on x, and so the partial with respect to x of f of xy gives us a 0 for that integral. And then for the second integral, we get the derivative, or the partial with respect to x, of the line integral over C of f dot dr. Now, writing down the components of f as pi plus qj, we get that that second integral is the line integral over C2 of p dx plus q dy. But remember, along C2, y is constant, so dy is 0, and we end up with, when we do some replacement using t as a parameter, ultimately the partial with respect to x of f turns out to be p of xy, because we're effectively differentiating the integral p dx. The punchline there is that p is the partial of f with respect to x. We could do the same thing for C1 and C2, where C2 is vertical. We'd get a 0 for, in this case, the second integral, and then we would also conclude that q would be the partial of f with respect to y. And the result is that f is conservative because we found a potential function f, lowercase f, for which the vector field f is the gradient vector. Now, I'm not naive enough to think that you absorb all that. I mean, hey, if you did, cool, power to you. But maybe go back over this and make sure that you kind of understand the details there. But we are going to move on. And we're going to jump right into another theorem. I said this section was heavily theoretical. If f of xy, a vector field, is equal to p of xyi plus q of xyj, and if this is a conservative vector field, where p and q have continuous first-order partial derivatives on a domain D, then throughout D, we have that the partial of p with respect to y is equal to the partial of q with respect to x. To prove this, we'll say that if the vector field f that has components p and q is conservative, where we have the continuous first order partial derivatives that we were stated, then there exists a scalar function lowercase f such that f, the vector field f, is equal to del f. That's what it means to be conservative. Thus, p is already a partial of f with respect to x, and q is already the partial of f with respect to y. By Clairaut's theorem, the partial of p then with respect to y would be the second partial of f with respect to y after with respect to x. Now that's not what Clairaut's theorem says. What Clairaut's theorem says is second mixed partial derivatives are equal. And so the second partial of f first with respect to x and then with respect to y, and that happens to be the partial of p with respect to y, equals the second partial of f first with respect to y and then with respect to x, which means that's the same thing as the partial of q with respect to x, because q is already a partial with respect to y. And that does it for the theorems that set up our work in this section.